Most of you who were in 605, you may recall we saw an existence uniqueness theorem for ODEs. And we're basically piggybacking all that for existence uniqueness for at least first order PDEs. Okay. So I'm just going to go ahead and state the existence uniqueness theorem. All right. Okay, and since I'm not uploading a video while recording another, hopefully we shouldn't have any technical problems. Okay, so a theorem statement is this. So here's our initial value problem. Okay, so AUX plus BUY equals C. And this is a quasi-linear PDE. So A, B, and C are all functions that depend on x, y, and u. So if it was just x and y, that'd be a linear equation, but we can be a little more general than that. And then, to complete the problem, we have an initial curve, which I'll call gamma. So this is a general initial curve that has these parametric equations. So x, y, and u, when tau is equal to 0, are all given functions. So basically, A, B, C, and these functions, x naught, y naught, u naught, those define the initial value problem. So A, B, and C define the PDE, x naught, y naught, u naught define the initial conditions. So once you have that, when does this have a solution? When is it unique? So this IVP has a unique solution, guaranteed, but this is only a local solution. So we're looking at values of tau and s where so tau is in some interval around 0, and s is in some interval around some point s naught. And no, these are not the same delta epsilon from limits. Just a coincidence. Okay, so in other words, we're looking at least points that are sufficiently near tau equals 0 and s equals s naught. So it has a unique solution if and only if the transversality condition is satisfied. And that would be meaning that the Jacobian, which I'll define as a function of s, which is a of, a y sub s minus b x of s. And I want to emphasize that this determinant has to be evaluated on the initial curve, because basically all of these are everything here is a function of tau and s. So because we're on the initial curve, tau has to be 0. And then s is allowed to vary. So this Jacobian has to be non-zero for s in this interval. S naught minus 2 delta, S naught plus 2 delta. So we need a little extra padding here. So as long as this Jacobian is known to be non-zero in a neighborhood this big of S naught, at least in a neighborhood half that size, you can guarantee that this initial value problem has a unique solution. Okay, so so bottom line is, as long as the initial curve, because this is a geometric meaning of this condition. The initial curve is not tangent to a characteristic curve. Okay. All right. So, because what's happening is, normally you have some initial curve, like maybe the x-axis, and you have characteristic curves emanating from that initial curve. So they should be going in independent directions, linearly independent. If not, the problem doesn't have a sensible solution. Okay. Now, I'm not going to go through a proof of it here. It's actually not really an interesting proof, for one thing, because it uses the existence uniqueness theory for ODEs. Because what does the method characteristic do? It breaks the PDE down into a number of ODEs, and you have to make sure that those have a unique solution. Now, I should mention, this is a technicality, these coefficients A, B, C, they had to be differentiable. Just to satisfy these, because A, B, and C are the coefficients, those are the time derivatives of your ODEs. So they have to satisfy the existence uniqueness theorem for ODEs in order for all of this to be valid. Okay. So it's basically because you have a unique solution of these ODEs around tau equals 0, that as long as you have this as well, you can guarantee this unique solution of the IVP. Okay. Now, I want to take a little time to talk about what can go wrong. So what happens when this transversality condition is not satisfied?
I feel like every time we answer a question wrong, you should draw a little hangman dude on the camera. It looks like a little hangman thing. You know the game, hangman?
Oh yes, yeah. Actually, what I found from playing Hangman with Diana, I know it's a really good word to stump somebody on in Hangman. Believe it or not, it's a rather short word, Xerox.
Oh, because now I guess it's X.
Yes.
We used to play it with like categories.
Why would I not? Like, if the Z doesn't work, it's Ero, and you think Eros, and then you try. If you have options, you do X, and then you win.
Yeah, for some reason, word just totally nailed me, but yeah. Go figure. Oh, try it.
Well, if you get ERO, then. Like,
Yeah, but you have to get that
E,
word.
Yeah, if you just get E, then yeah, right.
Because it depends on how quickly you to drop a hangman guy. So, how many body parts he has?
I'm never playing hangman with you.
Okay. Okay.
He ruins like every game. You do. You do. And he called me a nerd earlier.
How many games have you played with me?
None, but I'm still not playing any. Well, maybe soccer.
So then that's
I'll play soccer.
Anyhow.
yeah, right.
I'm sorry.
So, what if the transversality condition? Now, the thing is, here, we're not going to talk about when transversality is violated at a single point. But what if this determinant is 0 in an interval? So what's happening in this case is, so for instance, here's your initial curve gamma. Here's your hangman. So in a case like this, like so here's the characteristic curve. Maybe you have a characteristic curve like this that just barely touches it. So there we have JS 0 only at a certain point. So that is not the case I'm talking about. So something like this, where you have here's your initial curve, and your characteristic curve totally syncs up with it for a stretch, or maybe the entire domain. Maybe the curves are exactly the same. Okay. So so this is a characteristic, and this is gamma only in the xy plane. Because remember, initial curve, as I defined it over there, is in 3 space, x, y, and u. I'm not talking about that either. This is in the 2-dimensional space, xy plane. So characteristic is a projection of a characteristic curve in the xy plane. So that's one thing is we kind of have to keep straight, but this is the terminology the book uses. Characteristic curve is 3-dimensional concept. Characteristic is a 2-dimensional concept. Now the thing is, if you look at the definition of the Jacobian over there, it only deals with x and y. There's nothing about u in that transversality condition. So what's happening is, if j of s is equal to 0 in an interval, then at least in the xy plane, we have an initial curve and characteristic totally coinciding for a stretch. So the question then becomes, what happens to the solution in that case? Because now the existence uniqueness theorem is not satisfied. So there's 2 possibilities. One is, if you look at the characteristic and the initial curve in 3 space, you can go ahead and check the u values on the initial curve versus the characteristic. So if the u values do not mesh with numbers, so we have this agreement in 2D, but in the 3rd dimension they don't agree. You have no solution at all. You have non-existence. Because what's happening is you have u values in conflict. The solution is like multi-valued. The solution needs to be single-valued to exist. Okay. The other case that is more interesting is if the u values do agree. So that means that your initial curve gamma equals a characteristic curve in all 3 dimensions. Then you have existence, you just don't have uniqueness. You actually have infinitely many solutions. Okay. Not only that, you actually have a way of finding the infinitely many solutions. So in order to find them, you solve the initial value problem again with a different initial curve. I'll call it gamma prime. That any initial curve gamma prime, should be a prime there, that passes through gamma at a point. But again, it should not be tangent to it. So they just cross each other. Okay. All right. Now, this only covers the case where transversality is violated on a whole interval. If we have this situation, transversality is not satisfied at a point, yes, you don't have a unique solution. But it's a lot harder to make, you can't really make general statements like this about the behavior of a solution. It just depends on the particular. So I'm not going to go into that. We can't just make any blanket statements there. But what I can do is now I'm going to do an example of just illustrate what happens if transversality is violated everywhere, and show you how you can have a situation of non-existence or non-uniqueness.
So you mean to say for the infinitely many solutions part, the points at which that happens, gamma prime passes through gamma, those points are the solutions?
Basically, yes. In other words, you solve those infinitely many IVPs, and those, I'll show you. Okay. Okay. So for example, we'll have du dx plus du dy equals 1. And we'll solve this with two different initial conditions. So the first one, very strange one. So the initial curve is all points with equal coordinates. So it's basically like the line y equals x. And the initial value is also going to be x. Okay, so we solve this using the method of characteristics. So the characteristic initial value problems, so we have dx d tau is 1, the coefficient here. dy d tau is 1, the coefficient here. And du d tau is 1. How boring. And then the initial values, x naught of s is s, y naught of s is s, and u naught of s is also s. Very repetitive. So we only need to solve one of these. So x and y and u are all equal to what? Yeah, tau plus s. Okay. So what happens is the characteristic curves because remember, tau is a parameter for moving along a characteristic curve. So you're starting at some point that's SSS in the three-dimensional space, and you move in a direction 1, 1, 1. So the characteristic curves are straight lines. The direction is 1, 1, 1 because those are coefficients of tau. Along the line, x equals y equals u. So your characteristic curves start at a point of this form, and they continue to be a point of that form. So in other words, it equals gamma. So all you have is one line of all three coordinates equal. It is the initial curve, and it's also every single characteristic curve. And you can say that there's a different starting point, but they're all contained within the same line. So it's a very boring picture compared to what you have usually. Okay, so because the characteristic curves are exactly equal to the initial curve in all three dimensions, that means you have infinitely many solutions. Okay, so what you can do is go ahead and solve it again. So we let ux plus uy equals 1. And now for our initial condition, I'll specify u of x0 equals f of x. So slightly more interesting case. So now these ODEs will still be the same. But now your initial values will be different. So this will be s, y naught will be 0, and u naught be f of s. Okay. So now we can solve all of these. So x is tau plus f like before. Y is equal to just tau. And u is equal to tau plus f of s. Okay. Now, so how can I express the solution in terms of x and y? Basically, I need to invert this. So how can I express tau and s in terms of x and y?
Oh, it's not. S is x minus y.
Yeah, x minus y. So now I can fill that in. U of xy is equal to y plus f of x minus y. So I now have solutions, infinitely many solutions of this form. However, I have to be careful because I need to make sure that this solution also satisfies that initial condition. So what happens if I plug in this initial condition into here?
Yeah. Well, you get f of 0.
Right. And
f of 0 has to be 0.
f of 0 must be 0. So that is one limitation. So, but you can pick any function for which f of 0 equals 0 and use it. And that gives you infinitely many solutions. So I kind of deliberately left that out to the end. And actually, you can figure that out back here. Because suppose, because what I need to have all three of these equal each other. So for instance, if y is already 0, and if s is 0, then f of 0 has to be 0. So it really comes from here. So f of 0 equals 0 to match the original gamma, because this initial curve must pass through this one, and it passes through it to 0.000. Okay. So as long as you have that, then these are your infinitely many solutions. Oops, wrong notes. Questions on that one? Right. Now, let's change to a different initial condition now. Instead of u of x equals x, I said u of x equal 1. So in that case, I go through the same old process. So x and y are still equal to tau plus s, but u is equal to tau plus 1. So what happens is your Jacobian is still equal to 0 everywhere, because that's what you'd find. Because the Jacobian is a derivative of y naught with respect to s minus b derivative of x naught with respect to s. Well, a is 1. Y naught is equal to s, so its derivative is 1. B is 1, and derivative of x naught with respect to s is 1. So at all points, transversality is not satisfied. It's 0 everywhere for all values of s. So that's true from the beginning of this example. But the problem is your initial curve is S1. So you have the line y equals x but your u value is constant. So if you look in three-dimensional space, it's contained within a plane. And your characteristic curves so what we have is tau plus s, tau plus s. So for any given s, your y and x values are still equal, but your u values are also changing. So this is a key. Look at your u values. Constant, not constant. So they disagree. So in that case, there's no solution. This IDP cannot be solved at all. Because your characteristics and your projections of your initial curve are all the line y equals x. Identical everywhere. But without the u values agreeing, nothing you can do. Questions on that one? Okay. These are things that can go wrong with this uniqueness. It all boils down to how does the initial condition relate to the PDE? Like I said before, for any PDE, you can find an initial condition for which a problem can't be solved, or maybe has infinitely many solutions. Okay.
So your only options are either no solution or infinitely many. You don't have like an in between.
No.
Give it one solution.
Well, that's when transversality is satisfied, and that's when you have a unique solution. Yeah, when transversality is not satisfied, you're in one of those no man's lands.
Oh, okay.
Yeah. Okay. Okay. Now, after spending all this time talking about method characteristics, we're going to leave it for now. And we're going to look at a very different approach. Like, method characteristics actually is due to Hamilton. And we're going to look at method due to Lagrange. So it's actually called Lagrange's method. Okay. So it's kind of weird that Hamilton did not have method characteristics named after him, like Hamilton's method, but go figure. So a quick comparison of Lagrange's method and method characteristics is, okay, so first, method characteristics is very broadly applicable. You can use it to solve a wide variety of initial value problems. However, it requires the initial conditions. It's an integral part of a solution process because you need that to define your characteristic initial value problems. So if you don't have an initial condition in hand, you can't even start. Now this is at odds with what you saw in your first differential equation class, like 285. You'd be given the ODE, you would come up with a general solution for it, and then if you had initial conditions, you could fill those in and determine your constants. The method characteristics are not like that. On the other hand, Lagrange's method, the idea behind it is it can be used to find general solutions, which is quite nice to have a general form of solution without any initial condition specified yet. So you can say, okay, at least all solutions are of this general form. Unfortunately, it's not very practical, except for certain special cases that work out nicely. Okay. So there's a significant trade-off between the two. Okay. So what I'll do, so one of the homework problems from chapter 2 is using Lagrange's method. So I'm going to step through a general method and give you an idea of why it works, and then I have an example. Okay. So we have our general quasi-linear PDE, and I'm not going to bother specifying any initial conditions. Now, so again, A, B, and C, like before, may depend on X, Y, and U. I'm just too lazy to write that. Okay. So the first thing you do to carry out Lagrange's method, and it's very hand-wavy here. It's like, well, there's a lot of ifs involved. But this, like I said, this is the sort of thing where maybe you get to work for an example, but a lot of times it just might not be practical. So I'm going to define a vector field, P, that has components from a PDE, A, B, and C. Okay. Now, here's the semi-miraculous part. What you need to do is you need to find vector fields. I'll call them P1 and P2. Well, I'll give specific notation. P1 will have components A1, B1, C1, and P2 is A2, B2, C2. So you need to find vector fields that satisfy these two conditions. First of all, each of these vector fields must be orthogonal to P. So each PI dot product with P, which would be AIA, BIB, plus CIC, must be 0. So PI and P are perpendicular to each other at every point in the domain. Okay, and it's not, for a specific example, it's not too hard to achieve because a lot of times what you could do is, as a convenience, you can make one of these components equal to 0. Because if you have a two-dimensional vector field, it's very easy to come up with a vector field that's orthogonal to it. You just switch the components to negate one of them. So you can use that trick and then make a third component equal to 0. So that part is not bad. So that's one condition. The second condition, now, it's a lot harder to have this satisfied at the same time. So all of these two vector fields, both of them are exact. And what I mean by that is, there's two ways to state it. Its curl must be the 0 vector, or the more practical condition, each vector field is equal to the gradient of some function that I'll call psi sub I. So we have psi 1 and psi 2. Those are scalar value functions. You take their gradients and you get these vector fields P1 and P2. Because if you're not careful, you might be able to come up with these P1 and P2 that satisfy the orthogonality condition, but then you find that they're not exact. So that you can't represent it as a gradient of some function. So then you're kind of going back to the drawing board, as I actually had to do with working an example. So this is where a method gets a little bit hocus pocus. And it's because of this that it can only be used in certain special cases.
Curl the
I
dot
was-
product
Oh, we're gonna ask what curl means.
with
Yeah.
the gradient.
Curl is from multivariable calculus. The curl of a vector field f, and I'll let f be equal to a, b,
With
c.
gradient dot product with the right?
No, it is the
Is it
cross product.
Okay, cross product with the gradient. Okay, with that. Okay, that's the
yeah.
divergence.
So it turns out to be, in terms of these components A, B, and C, you get C, Y minus B, Z AZ minus CX, BX minus AY. So that's the formula for a curl. If a curl of a vector field is 0, it means it's irrotational. There's no spin going on. Because the physical interpretation of a curl is at any particular point, it's a vector. So the direction of a vector is an axis of rotation. So and the magnitude of a curl is a tendency of a vector field to swirl around that axis. So if a curl of f is 0, there's no axis and there's no rotation. Actually, another term for exact vector field, we also say it's a conservative vector field. In fact, that's the term I used when teaching this in Cal 4. Okay.
There was like green steering wheel, right?
Yeah, it comes up there. Yeah, all those vector calculus theorems. Okay. And the thing is, how hard or easy it is to do this, it just depends on the specific case. Okay. All right. Now I should mention that if you recall from ODEs, you can solve some of those using integrating factors. Like you can check if the equation is exact. If it's not exact, use an integrating factor to solve it. And this is an attempt to generalize that approach to ODEs to PDEs. But the thing is, you're now going to a higher dimension because you have more variables. Instead of just x, you now have x and y. And that's why, as you try to go to higher dimensions, this gets a lot harder. Okay. Okay, so at this point we're going to assume that this was possible. Then what do you do? And why should this even be helpful? Okay. So what happens is, once you have a function psi1 and psi2, the next thing is you have the surfaces psi1 of x, y, u is equal to a constant, which I'll call alpha 1, and then psi2 x, y, u is equal to alpha 2. So these define families of surfaces, because alpha 1 and alpha 2 you can think of as constants. So for each constant I choose here, this equation defines a surface in three-dimensional space. So what I have here is two one-parameter families of surfaces. Okay. Now, suppose I choose particular values, alpha 1 and alpha 2. So now I'm dealing with two specific surfaces, one from each family. So I'll draw the situation. So here's one surface, so psi1 is equal to alpha 1. And then we have another surface, so psi2 is equal to alpha 2. So generally, these surfaces are going to intersect, and the intersection is a curve. Just like if you have two planes that intersect, that intersection is a line. And I'm going to define this curve parametrically, x of tau, y of tau, u of tau. Okay. Now, so here's where we get close to an actual solution of our PDE. Now, psi 1 and psi 2 are both constants along this curve, x of tau, y of tau, u of tau, because they're equal, like psi 1 is equal to alpha 1, psi 2 is equal to alpha 2. So what that means is the derivative with respect to tau of psi 1 of, so I'm going to plug in the curve into the surface function, has to be 0. Because along this curve is contained within the surface. Actually, this is not just psi 1, psi I, for any I, 1 or 2. Okay. Now, suppose I go ahead and work out what this derivative is using a chain rule. Well, this equals, if I have a chain rule, this is the gradient of psi I dot product with the tangent vector of this curve. But that's just x prime, y prime, u prime. And that has to be 0. Now, what's the gradient of psi I?
0.
No.
That P.
P I.
Here.
Yeah. So, in other words, the tangent vector, x prime, y prime, u prime, is orthogonal to the vector field pi. But the thing is, what else is orthogonal to pi?
P.
Yeah, I define p1 and p2 so that they're orthogonal to p. So I can say, in other words, putting it, the dot product of these is 0. So what that means is P is actually parallel to this tangent vector.
They have the same gradient.
Yes. But the thing is, what is P? P is a vector field. P is a vector field ABC. But the thing is, what are x prime, y prime, and u prime? These are. So in other words, x prime, y prime, u prime are multiples of A. Actually, I can't use C here. I need a constant.
K. Oh, you're right. 2-1.
What else was suggested?
She said M.
Oh, M is like for integers. Well,
M, J, and M. Well, so is K.
Yeah.
K's flexible.
Use use D. I always use D because it never gets used.
Constant is K, right?
It never gets used. Or D.
Or maybe mu.
Use an A. No, big A. Never mind.
Stop it. Okay. All right.
So is it going to be the same K throughout?
Yeah, it's parallel.
Parallel.
This vector is a multiple of this vector.
But by the same one, it has to be 3 times or something.
Yes, same
that
constant.
makes sense.
Yeah. So what that means is this curve x, y, u of tau is characteristic. In other words, it defines a solution of the PDE. Right, so that's the key to Lagrange's method. Why we need to find these vector fields P1 and P2 that are orthogonal to P and exact, so that we get from those, we get intersecting surfaces. The intersection of surfaces give us curves. Those curves are the characteristic curves that the method of characteristics would give us if we were doing that. Okay. So the last step in defining the solution, the whole point of Lagrange's method is to get a general solution. And this will become a lot more clear when I do an example in just a little bit. Okay, so if I let alpha 1 and alpha 2 vary, okay. Okay. So suppose I have a curve in my parameter space, alpha 1, alpha 2. Because what I did here was I picked specific alpha 1 and alpha 2 and got a characteristic curve. So I can choose any alpha 1 and alpha 2 and get another characteristic curve. So if I have any curve within alpha 1, alpha 2 space, it could be anything. So each one of these points along this alpha 1, alpha 2 curve gives me a characteristic curve for my PDE. So any such curve can be defined by an equation of this form. Some function big F of alpha 1, alpha 2 is equal to 0. So in this case, we have the curve defined implicitly. An alternative can be something like explicit, alpha 1 equals little f of alpha 2. You could do that too, or vice versa. So there are many ways to represent curves. I'm using this one because this covers everything. All curves can be defined at least implicitly. So that way you can have like vertical tangents and stuff. So now I can finally describe a general solution of a PDE is of this form. Some function of psi 1 of x, y, u and psi 2 equals 0. So, and f is an arbitrary function. It's psi 1 and psi 2 are the specific things you have to come up with. So, big F, what is that? That depends on whatever initial condition you have. And the thing is, we didn't use initial condition anywhere in this discussion. So it just comes into play at the very end. Just like what you're accustomed to for ODEs. You use some method like integrating factors or solving characteristic equation to get a general solution. And then the initial condition doesn't come into play until the very end. So this is more like that.
So that's a general solution. When you have initial conditions, you have an exact, like a unique solution.
Yeah. So what you do is you can have an equation like this. So then you go ahead and fill in your initial condition for x, y, and u. And this, and the thing is, how do you? So everything, these arguments are now completely filled in, and now you need some sort of equation that makes it equal to 0. Okay. So all right. So now I'm going to work an example, and you can see how Lagrange's method works, and you can also see why it's so specialized and only usable in certain nice cases. So hopefully the one homework problem I gave you won't be too much of a bear. But we'll see. Sorry, I have a student meeting me right after class. And apparently I have to tell them where my office is twice. Okay. Okay, so here's my PDE. So minus y u dx plus x d dy, 0. Okay, so my coefficients, A is minus y, B is x, and C is 0. So my vector field P is minus y, x, and 0. Okay, so now I need two vector fields that are orthogonal to this one. Fortunately, this is like basically a two-dimensional vector field, because with just a zero component added on. So that makes things a lot easier. Like I said, very specialized method for nice cases. So, like I said before, this is a very good trick to know. If you have a two-dimensional vector field, in order to make an orthogonal one, switch for components and negate one of them. So for instance, x, y, 0 is going to be orthogonal to this. So you can see you take a dot product, you get minus xy plus xy is 0. Will be another vector field. Sorry, what? Yeah, but that's still linearly dependent on this one. So, but the fact that we tacked on this third component here, how can we take advantage of that to get a number one?
Can you swap the last two? Never mind. Never mind. This is linear. No.
What?
Or x, y, and sometimes z. I mean, something like that, right?
Because what you could do is you could just make these components 0.
Leave the last one the same? No. Well, never mind.
Okay. Well, actually, you could have put anything here,
Right.
but you might as well pick the simplest thing. Okay. Now, the next question is: are these exact? What you can try to do to one way to check it, you can take for a curl, but another thing you can do is go ahead and integrate this with respect to x, this with respect to y, and this with respect to u, and see if you can get everything to match up. So this is the gradient of psi 1, where psi 1 is like integrate this with respect to x, and you get 1/2 x squared. Integrate with respect to y, you get 1/2 y squared. Whoops, that's x squared. And then you integrate this with respect to u, you get a constant, but we don't need to fill in arbitrary constants here. There's no point in having those. So
You integrated with respect to x, right? Just x? Or
Um,
both x and y?
x, y, u.
Oh, okay.
Yeah, because now you can see if you differentiate this, with respect to x, you get x. With respect to y, you get y. With respect to u, there is no u here, so you get 0. What about this? What would this be the gradient of? Just u. Because you differentiate with respect to x or y, you get 0. Differentiate this with respect to u, you get 1. Alright. Because what you do is,
Oh, yeah, I thought you said integrate.
Yeah, but
well,
it's
no,
not zeros.
to go from here to here, you integrate. To check this,
Oh,
you
you check.
differentiate. Yeah.
Okay. So,
Yeah.
so you're saying you need the constant at all, basically.
Yeah.
Okay.
Yeah, so just a reminder, integrate each component with respect to the corresponding variable.
Right.
But if you get a constant, just throw it away.
Okay.
Okay. All right. So these are the simplest functions that would work. Okay. So now we have psi 1 and psi 2. That was actually the hardest part right there of the actual Lagrange method, because actually, when I was working a different example. Getting orthogonal vector fields was no problem. Then I tried to integrate and find like, oops, it's not exact. So I had to go back and try again. Okay. So to define a general solution, okay, I can use a simpler form that I used on a previous board. I'm going to let alpha 2 be an arbitrary function of alpha 1. Okay, so you have some curve in your parameter space. Okay. That means your general solution is going to be psi 2 is equal to an arbitrary function of psi 1. So now you just fill in what it is. And I could have gone the other way. Alpha 1 is a function of alpha 2. But psi 2 is equal to u. And so if you could have an explicit form like u equals something, of course you want that. So u is a function of But actually, 1/2 doesn't really matter because you can just absorb that into f. So any function of x squared plus y squared is a solution. And that's it. That's your general solution of your PDE. And to confirm this, well, du dx is f prime times 2x, and du dy is f prime times 2y. So now if I have minus y ux is equal to f prime, or so minus f prime 2xy, and xuy is equal to f prime also times 2xy. So then you add these together and it cancels out and you get 0. Okay. So if you're able to find two orthogonal exact vector fields, then you're basically done. And so actually explaining why the method worked was took more time than the method itself. Okay.
Are those big F's down there? Little F's this time.
Those are
To the
little
bottom
f's.
right. Bottom right. Bottom right. Those are little F's?
All these are little f's.
Oh. Okay, one more time. Okay.
Okay. For one homework problem, I did work it out. You can find the orthogonal exact vector fields. It may not be your first attempt that gets it, but it is doable. So, and what I described before, like working with two-dimensional vector fields, like swapping a component and getting one, you can try it with like the first two, or the last two, or the first and third. Like you can try different combinations like that, and get it to work that way. So those are what I would go with first, to try to get the right kind of vector field you need. Okay. Questions? I've actually run out of notes. So, yeah, exactly. Do you have more homework questions, or has anyone else touched homework too?
I looked at it.
Oh, okay.
Numbers.
It's not due for 3 weeks.
I know. Yeah. Well, now you can do after this section. You can do all the problems except the last one. Actually, I have. Okay, I think I have 2 lectures left on this chapter. So it's a long chapter. Okay.